Good evening, everyone. It's my privilege to welcome you all to the anniversary celebration of Share Genes WhatsApp group. A year ago, Share Genes began with a simple belief and idea that knowledge in genetics and plant breeding should be freely shared. Today, that idea has grown into a vibrant community of 592 members with over 500 actively visiting the group on a regular basis. Till date, we have shared 132 media posts, 64 documents, 85 useful links for the benefit of all. And in addition, we have shared 7 scientific news and updates, 21 interesting facts, 16 inspiring quotes, and 7 concept notes, and 4 debatable concepts, 5 notelets, 3 short notes, numerous opinion polls, and lively discussion that have kept curiosity alive. And yes, even 2 Sudoku games and information on the unsung heroes of science was shared. And recently, we have initiated the Share Genes Knowledge Lecture series on Mendel's birthday, and this is our second lecture. My humble request to all the members is to actively share information. Please don't think that this group was created by someone else and so only they should contribute. This is not the purpose of Share Genes. Okay, this platform belongs to all of us. Every fact, article, research paper, news, updates, and observation we have you shared adds values to entire community. Even a small piece of information can spark curiosity and start a discussion or help someone learn something new. I sincerely urge each one of you to contribute whenever you come across anything relevant to this subject. My vision for the Share Genes is to become a self-sustaining voluntary group driven by the passion and commitment of its members. Consider this group as a platform to show your love and gratitude for the field of GPV and as that has brought to you this far, whether by choice or by chance. And the moment you disappear from this world, your wisdom and knowledge fades away with you unless you shared it with the world. Let's all work together to keep the spirit of knowledge sharing alive and growing. Our motto, the Jnanadanam Mahadanam, says it all, and share the genes of knowledge because truly knowledge grows exponentially when it's shared. As we celebrate our first anniversary, I sincerely thank each one of you for making this group a so dynamic, collaborative, and inspiring. And I am delighted that we mark this special day with a special lecture. Now, let's begin. Let me introduce our speaker, Dr. Anilkumar C. Dr. Anilkumar C, sir, served as a scientist in genetics and plant breeding at the Crop Improvement Division, ICAR-Central Rice Research Institute, Cuttack. His expertise lies in the quantitative genetics and marker-assisted rice breeding. Through his research, Dr. Anil sir has been working on to bridge the classical breeding knowledge with the modern genomic tools, with a focus on improving breeding efficiency and accelerating varietal development. Today, he will share his insights on genome-wide selection, an approach to enhance the breeding efficiency in crops, a topic that promises to open new perspective for breeders and researchers alike. Please join me in warmly welcoming the Dr. Anilkumar sir. And before initiating the lecture, I have 2 announcements. This meeting is limited to 100% participants. If your friends are finding or colleagues are finding difficulty to join, please inform that the lecture is live on our Share Genes YouTube channel. And I request all the participants to mute their microphone to avoid the disturbance during the lecture. And you can post your questions in the chat box. At the end of the session, a few selected questions will be shared with Dr. Anil sir for the discussion. Thank you. Sir, handing over to you.
Thank you, Ravana. Thanks for having me here today on this prestigious occasion on sharing my knowledge that I gained in the past 5 years in my rice research. So I'll be sharing. Can I share my presentation now?
Yes, sir. Yes, sir.
Yeah. I hope this is visible to everyone.
Yes, sir. It is visible.
Yeah. From the past 5 years that I gained the knowledge on this topic, that is genome-wide selection, commonly called genomic selection. So why it is so important and how we should understand this in crop breeding. Why it is so important when we work with a complex traits like quantitative trait that involves yield also. So what we do, the breeders do is first we choose parents and we cross and we produce progenies from that cross, and we select the best progeny, and that progeny may be released as a cultivar, or we use that as a parent for the next cycle of the crossing or hybridization to produce next base population that will give us our best progenies to release. But when we are working with a complex traits, we have so many things unknown things. So when we are working with the quantitative traits, we don't know how many number of genes are responsible for the trait that we are working, and where those genes are located in the genome. We don't know exact position of the genes that are located on the chromosomes. Yes, nowadays we have a technology, we can find the QTLs are the genes that are on some chromosomes, but it's not possible to find out all the genes that are responsible for the trait. And we also don't know the effect of each gene that is contributed to the trait. When we do QTL mapping, we identify some QTLs, or when we do GWAS, we identify some associations with limited effect or limited phenotypic variation explained by that marker or the QTL that we identify. But it's not sufficient to address the complete quantitative trait that we are working with, because when we say quantitative traits, it is not, the trait is not alone, it is also contributed by auxiliary traits or contributing traits. Say example, yield. When we say yield alone is not a trait, it is having so many traits contributed to express itself. And being said that, there are many genes that are contributing to the yield and the contributing traits. And when we want to improve the yield, we have to improve all other traits, which is not possible in a one go. We have to work simultaneously. We have to do some parallel breeding to improve each and every trait that contributes to our final trait. So how we can improve these traits? Earlier, what we used to do, the one of the good breeding approach in a traditional system was the recurrent selection approach. What we were doing in the recurrent selection, we used to choose some good parental lines and made them, get the progenies, evaluate them. From them, we select some best performing progenies, again, intermediate them, go for the another cycle. And like that, we used to continue that breeding cycles for several years to find out best performing progeny or best performing candidate that can be released as a variety. In that process, breeders used to spend lot of time and lot of resources. It again, the gain that we used to get was limited in the sense, the gain and the time that we spent were not correlated, because gain was, yes, we used to get good gain in the recurrent selection, but the resource spent on that process was really much more. So for that, the breeders wanted to have another approach, any ad hoc approach, where we can get the maximum yield for limited time. So then breeders looked into their breeders' favorite equation, where time was a new component added in the breeders' equation. So we wanted to see gains in every cycle, every time period we spent on that cycle. So that's why breeders targeted towards this time also. When we say breeders equation, we always look into the gains, genetic gain. When genetic gain is contributed by so many components, including the selection intensity and how accurately we are selecting the good progenies, and what is the genetic variance we are maintaining in our breeding program. So now, if I go back to my recurrent selection program, traditional recurrent selection program, when I do this mating every cycle and continue several cycles, the genetic variance that I'm keeping in my breeding cycle, it goes on breeding program that goes on decline after cycle. So it's important to have genetic variance when we plan for the long-term breeding programs. So for this, there was one approach. Now recently it's become so famous, and that is called genomic selection or genome-wide selection. Yeah, I use genome-wide selection. I'll tell why I'm using this genome-wide selection. It's not a new approach. It was borrowed from animal science. Why it is borrowed from animal science? How it is evolved in animal science? Animals, we know they are not hermaphrodites. They have genders in them. So genders of animals need to be crossed, and those animals produce only few progenies per grass. And it is not like plants having hundreds of progenies to go for QTL mapping or selecting, doing that one. It's not possible. And there are many other traits in animals. Say, milk is a good example. Only female produces milk, not the bull. So selecting for the high milk production, it's not only selecting the female, we have to look for a good male country, this combining male also. So what this animal breeders did, they looked into their relatives, progenies, and the parental relationships. They used those relationships to identify best performing progeny or best performing female cow that can give more milk. So this was the approach where relationship comes first. Relationship is the one criteria that makes the selection more effective. Same concept was brought to the plants by Professor Rex Bernardo in maize, where he used genome-wide markers and marker-based relationships between the progenies and the pedigrees. So from that, he predicted performance of single-class maize hybrids using the information from the related hybrids. That was in 1994. When I say this, 1994, we don't have any option to say it is a new technology. It's already been 30 years old. But when it was not so much famous when he published this paper in 1994. After that, Mewson and his team, they published another paper that where they estimated the genetic value, total genetic value of the individuals in 2001. Then became very much famous. So now everyone knows it is more effective and more important in breeding for the quantitative traits. Why it is so important? So if you see this four-faced figure, you will understand this much better. So this was developed by Rex Bernardo. I must be thankful to Rex Bernardo for producing this kind of figure. So if you look into this one, there is one phase with number of loci controlling the trait, and there is another phase, purpose of QTL mapping, why we are mapping the QTL. There is a bottom phase, there's approach we use, and the other phase is germplasm. Now here in this, I just want to focus on the phase that explains the number of loci, and the other phase, the marker-based selection approach. If you see here, when there are number of loci are very less, we have so many approaches, which in breeding, these approaches can help in introgressing the QTLs into a elite background to produce candidate lines. And if you say intragress breeding, introgression of major QTL or intragress breeding, it's a kind of first it's a defect correction or a pre-breeding approach. And that is possible when you have a major gene or a major QTL that can be identified through QTL mapping or cloning, anything. And they know most popular, recent popular genome editing is also comes under this approach, where it can be added below this mapping the major QTL. So there, if you are in your trait is having few more genes, a few more loci, or number of loci are increasing, our approach, breeding approach, can be improved to enrichment, F2 enrichment, or base population enrichment, where we can bring in new variation and improve our base population. It can also be done with the with using the molecular markers. Again, if your loci are increase more, we can look into the marker-assisted recurrent selection, where when we know more number of loci and the markers associated with those loci, we can select for those loci using the markers and improve our populations. But this is possible when you have a number of markers that are associated with the loci. But when you say quantitative traits, number of genes we don't know, it is so many, a numerous number of genes are contributing. In that case, we don't know how many markers are associated. When we don't know associated markers, it's not possible for the Mars to go for. So the best suitable approach is genome-wide selection. Again, genome-wide selection, how it works is a question. So I use this figure to explain here. And this figure, Susan and Rex produced this figure for the different purpose, but I feel this is the best figure to explain the how this genomic selection works. Rationale here is when I say genome-wide selection, we use genome-wide dense markers present on chromosomes. And the rationale is at least few markers on the genome and chromosome associate with the genes responsible for the trait of our interest. Maybe that may be direct trait or indirect trait. Say, for example, if yield is our trait, the markers may be associated directly with the genes responsible for yield, or markers may also associated with the contributing traits, and that markers can also help us to identify our best progeny, our best individual through this GWAS. How this works? Say, here is an example. We have two parents here which are contrasting. When I say contrasting, one parent will be having the superior performance and the other parent will have poor performance, whatever the trait is. It should be assume a quantitative, any quantitative trait. Here we have markers on this chromosome. I'm just considering one pair of markers in both the individuals. And these markers are distributed on these chromosomes. We have 4 markers here. If you see here, a marker 1 is positive in parent 1, but it is negative in parent 2. Other 3 markers are negative in parent 1, but positive on the parent 2. That means these markers are polymorphic between these two individuals. So what we do, we cross them, and just a second. Yeah, we cross them. When we cross, there will be recombinations and the segment exchange between individuals. And once we develop the double haploids or any homozygous lines through development of reels also, there is exchange of chromosomal segments and there is recombinations, reshuffling of genes occurs. See, here there are 6 individuals I consider here. Okay, so here if you see, there are 2 individuals, one individual with all the genes in negative effects, one individual with all the genes with the positive effects, and all of the rest of the individuals having mixture of positive and negative effects. So what genomic selection do here is it will select for this marker effects with the positive values. So the GEBVs, what we call genomic estimated breeding values, are the summation of this marker effects that we have here on the chromosomes. And the one individual that is having 1.8 is the highest genomic estimated breeding value among all the 6 progenies. Okay, so when we select using the genome-wide selection, we look for this individual which is having all the positive effects. Okay, this is a one highlight. That is one glimpse of this, how this genomic selection works. That means here the markers associated with the trait are the main criteria which we use here. Marker effects, that markers associated with traits, and the marker effects associated with the trait are used to select the individual. And we all know this framework. It's very common. Everyone knows this. The framework. Framework contains 2 populations. One is training, other one is the breeding or test population. What training population mean? Training population is the one population that is genotyped, phenotyped, and on which the GS model is trained. Phenotype means it's very important to go for precise phenotyping, avoiding a lot of error that is contributing to the trait expression. When we say quantitative trait, we know trait is also influenced by environment, and it's also, there will be a lot of error involved in that, and there will be a lot of interaction of genes that involve in the expression of the trait. So when we go for precise phenotyping, we are accounting for all the possible error that we can remove from the trait expression value. Okay, so that's what phenotyping should be very much precise in before training the model. And the genotyping, we don't have anything in our hand. We should the genetic markers that are SNPs or SSRs, whatever the markers that we use, genotyping will be same. Whatever the environment we are growing, that will not change. Okay, once you have this genotyping data and the phenotype data, then we go for training the GS model. I'll come back to that. What is that training the GS model means? And the next population is the breeding population or the test population. What this test population is? Test population is, we have only genotyping information, and the genotyping information means this marker information. The marker information should be similar. Same marker should be used between in the training population as well in the test population. So we have a genotyping information here and phenotyping and genotyping information in training population. The model that we build on the training population will be used to predict the values or predict the genetic value of the breeding population or the test population. Based on that breeding values, selection decisions will be made. What selection decisions? Whether to select that individual or reject that individual will be made based on that predicted genetic values. And there is no phenotyping in breeding populations or test population. Yeah, it is possible when you select, after selecting, you can go for phenotyping to confirm your selection is good or bad. So I said training the model, GS model. So here I'll show a simple equation. It's a regression equation. Training the GS model means GS model is just a regression equation, nothing more than that. So when I say training population, we know here you can see y is equal to mu plus x beta epsilon. So epsilon is error. Y is the phenotypic data points of the training population individuals. So it is a vector of its number will be total number of the individuals in training population that will be in a single vector. That is your phenotypic values. And mu is mean of the trait in the training population. So in training population, you have evaluated in multiple locations. You also got the phenotypic value of the individuals. Same way, you also got the mean of the training population. Similarly, the training population is also genotyped, right? So the genotypic values, genotype data information that is either in binary format or SNP format. Usually we use in a binary format, 0-1 format. And that value is presented here as a X. X is a matrix of genotypic values, where in each column we will be having markers. First column will be having the marker number 1, second will be marker number 2. Similarly, it will be up to marker number n, and this will become a matrix. And the beta is a vector of marker effects, which we don't know in a training population. That is an unknown in the training population. Epsilon is the error that can be neglected here because we are accounting for the additive values in the model. Okay, so now what we are estimating? We are estimating beta. In a training population, we are training the beta values. Beta is the marker effects that we are genotyped on the training population. Okay, once you train this beta values, we will be taking them to test population. What information we have in test population? Test population, we already know the mu value from the training population. And we also have X is a matrix of genotypic data, that is we have the same genotypic information on test population also, same marker values. And the beta is already estimated. Marker effects are estimated in training population. Now, unknown is phenotype. When we have other known components, estimating the one unknown is not a big deal. We can easily estimate from this equation, we can estimate the phenotype. So once we estimate this phenotype, how would you say this is accurate to the how accurate this phenotype is in the test population? What we do in training population, we go for training the beta using the cross-validation approach. But in test population, it is not the cross-validation, it is independent validation. But how to say this is accurate value? I would like to give a simple example. We all wear the cloths, right? So cloths, we nowadays nobody is going to tailor and ask him to take the measurements and stitch the cloths. But we go to ready-made shops and we buy the cloths in the shops or showrooms. So what we look there? We look for the sizes. What sizes we see? We see XS, S, or M, L, XL, XXL, like that. 6 or 7 categories, not more than that. But say if I take only India, we have 1.4 million people, but we have only 6 or 7 categories. Is it true all the people can fit into the same sizes? No. If I say medium, because I am medium, so I am taking that example of medium, it ranges from say 28 to 32, something like that, waist size. So when I say that, we have a range of sizes, 28 to 34. For a person who is 28, for him, it may not be perfectly fitting. It may be slightly looser, or the person 34, he may having slightly tight fitness. The in between person, they may be feeling comfortably perfect fitting. Like that, the values that we estimate on the test population will also have little bit variation. That's what we call accuracy of this prediction. And if there is slight differences, the accuracy will come down to 0.6 or 0.7. If it is perfectly fit, accuracy will be accuracy will be 100%. And in quantitative traits, it's not possible to have 100% accuracy. Why? Because it's also influenced by errors, environmental components, and interactions. Many things comes here. Epigenetic components, epistasis components, interaction components, many things will come here. But here we are focusing only on the additive components. Therefore, accuracy will never be 100%. So at least if we are getting 0.5 or more than 0.5, accuracy is really good for the quantitative traits. So this is what the prediction accuracy is. So now we have y values that predicted on the test population. This is how the genome-wide selection works. And what are those factors that's influencing this prediction accuracy? One most important thing is relatedness between test population and the breeding population. How this influences. Say if you're taking the measurements for the shirt and buying a trouser, it's completely different, right? When you take the measurements for the trouser, you have to buy a trouser. When you're taking the measurements for the shirt, you have to buy a shirt only. Taking measurements on the shirt and buying a trouser, it is entirely it'll never fit. So you may get some accuracy value, say 0.1, 0.2, something like that, but it's not the value of your trait. So something like that, similar to that. If you don't have a relationship between your test population and training population, the marker effects that you estimate on the training population will never fit into the breeding population. The values that you estimate will never account for the accuracy. It's not possible to get the actual phenotypic values of the breeding population if we don't have any accuracy between individuals. That's why in genomic selection, a relatedness is the most important criteria. How to measure this relationship? Earlier we used to use pedigree information as the relationship measurement. Now we have molecular markers, right? So it's very easy to account for. Anyway, both training population and breeding populations are genotyped. It's very easy to estimate the relationship between training population and the breeding populations using molecular markers. So if there is a good related relationship between training and breeding populations, your prediction accuracy will really increases. And the other component is your heritability, trait heritability. If the trait heritability is good, say 0.7, 0.8, what it means? It means your trait is controlled by additive genes, more of additive genes than any other influences like dominance, or any other environmental influences, other error things. If your heritability is low, means it says that you have other variations controlling your trait, like environmental factor or any other errors. That means your phenotype is having more of other components than their additive components. So if in that case, your training population phenotype will not be completely explaining the genetic value of the trait. So marker estimates that are marker effects that are estimated on training population will be false. So they will not completely give a good accuracy in testing population. So another component is number of markers. How many number of markers we have to use in the genome? So best criteria here is to look for the LD between markers. So LD between markers means how your segment of the genome, how the segment of your genome is uh, coming from the parents to the progenies, how big your marker interval is. If they are very close, then they are accounting for all the genes between those nearby genes that are controlling the trait. Another component is prediction model. Don't worry about this models too much, because one of his famous statistician, George Box, he says that every model, all the models are wrong, but some are useful. So even the simple model that we use, say ridge regression, that is good enough to go for good selection, using these molecular markers. So these are some components that are increase the prediction accuracy in the genome-wide selection. So that's the basic. I am coming to little bit applied. My idea here is to everyone should understand in a simple way how the genomic selection can be implemented, how we can go for which training population is best, which test population is good, and what stage we have to evaluate. All the things I try to provide very simple things in a simple manner. So which is a good training population? Whether we have to use the germplasm as a good training population or RIL as a good training population. So obviously, everyone says the RIL is a good training population. But when you say RIL is a good training population, your breeding, what is your breeding population? Breeding population should be part of your RIL population, right? Then in that case, the population that you produce, RIL population, maybe from one cross, maybe from two crosses. When you use more than one cross, there should be some relationship between the crosses. So that will contribute to your prediction accuracy. So when I say germplasm, your test population should be derived from the crosses that are developed from these germplasms. So what in this figure, you can see that we made some exercise to find out which is a good training population, was a germplasm or a real population. Obviously, real population shows really good prediction accuracies. To increase the prediction accuracies, real populations were the really good training population. But germplasm was not bad. Germplasm was also good. If you see among 4 models that we used, only 2 models showed significant differences in prediction accuracies between the training germplasm and real populations as training populations. But other 2 says it is okay to use germplasm also as a training population. That means if you're already having a breeding population, just look back into the pedigrees of the population from which you chose the parents, you can use them as the training population to build your GS model and select in the population that you have. So best among these 2 is the real population to use, but germplasm is not bad to use. How many markers we should use? Should we use thousands of markers? Is it required to use highly dense markers or very few markers? This can be decided based on the genome size. And this is an example from the rice that I'm showing you. The markers that I used in this study were SSR markers. I used the maximum of 300 markers in this study, but I wanted to see how this increased or low marker numbers can influence the prediction accuracy. So you can see from this figure. So when I reached 150 markers, prediction accuracy was more than 0.6 in some models. So that says they are using, so again, you have to remember when I say SSR markers, they amplify the large segments of the genomes, and the SNPs are just the one nucleotide differences. So we can say a 150 SSRs are equal to around nearly 700 to 1000 SNPs, polymorphic SNPs between in the population. So here for me, in this population, 150 SSR markers were found really good enough to go for genome-wide selection. After that, there was not significant increment in the prediction accuracies. So I would say that depends on parents, that depends on crop, genome size. So where you can see rice is a very small genome. So for me, it is 150 SSRs were good enough to go for genome-wide selection. But if you're working on any other crop where the genome size is too big, you may have to look for the LD between markers, average LD between markers. If your average LD is good, then that number is good enough. Or you may have to make some exercise to find out which is the good number of markers to use in the genome-wide selection. So another question is when to predict. Whether should I go for prediction in early generation, F2? F2 means it's a segregation generation, early generation, or should I select in F6? Which one is your option? Everyone says, yeah, it is good option to go for selection in F6. Why? because it's already fixed lines. All the genes are fixed in homozygous condition. So whatever you choose, that will be transmitting to the next generation as it is. It will not segregate. But when you choose in segregating generations like F2, the segregation or the genes will segregating in further next generations. So yeah, it is true. If you're choosing an F2, there is a significant differences will be there. So we did an exercise here. We did the selection in F2 and did the selection in F6. In the F6, out of 4 markers, we could see there are out of 4 models, 2 models showed significant differences in the prediction accuracies, predictive abilities, and other 2 showed non-significance. So non-significance, when I say non-significance, it shows some light, like we can use this we can think a different approach here. So what is that? Instead of selecting, is there any chance that we can reject inferiors in early generation? Yes, of course, we can think on that. We can use this early generations genome-wide selection to reject inferiors, many inferiors, and reduce the population size that can be forwarded to the next generations. So, but yeah, this is about the predictive abilities. And what about the genetic gain? If I choose an F2, is the genetic gain will be good? Or if I choose in RIL, genetic gain will be good? For this, myself and Professor Rex did an simulation exercise. What we did, we chose some breeding approaches. SSD single seed descent method plus genomic selection at F5, and FRGA is field-based rapid generation advancement plus genomic selection at F5, and genomic selection F2, genomic selection with the FRGA in F2, and 2 cycles of genomic selection at F2 in a FRGA method. What is this 2 cycles means? 2 cycles is cross 2 parents, generate F2, do a genome-wide selection, choose best 2 parents, cross them, develop a new population. That was the 2 cycles of genome-wide selection. Select the best in the second F2, second population, that is second base population, that is F2. For our surprise, genetic gain was good when we choose in F2 than in F5. This is because the number of individuals, progenies, will be drastically reduced when we choose in F2 itself. Only best performing individuals are selected. And in the genomic selection, we are accounting only for the additive genes, gene effects. So that makes good genetic gain. So we found the selecting in early generation is really, really significant, produce a significant genetic gain than selecting in late generation. So can we predict multiple traits together, or can we use correlated traits together? In the beginning, I was telling trait like yield, they're not single trait. They're contributing by many other traits, correlated traits, right? So we did an exercise with the selected for the single trait like yield, as like any other approach, genomic selection approach, where in training population, we had both phenotypic information and the genotype information. For the test population, we don't have any phenotypic information. We predicted the phenotypic information using the information from the training population. That was as like any other approach. In the second cross-validation approach, we divided this training population and the test population, we had the information for the secondary traits, not for the yield or not for our primary trait. We use the phenotypic information from training population and the phenotypic information of secondary traits in the test population. And we did the genome-wide selection for our primary trait. And the third approach was we used the phenotypic information from the training population, and the phenotypic information for any trait was not there in the test population. We predicted the primary trait using the phenotypic and genotypic information of primary and secondary traits in the training population. Can you guess what was the result? See, this was the result. When we use single trait approach and a cross-validation approach with the multiple traits, cross-validation approach 1, where we used complete phenotypic information from the training population And the phenotypic information of secondary traits in the test population was produced really high predictive abilities. And the other cross-validation approach, where we had phenotypic information of all the traits, including primary trait and secondary traits from the training population, and the no other information from the test population. So that was also having little better predictive ability than the single trait approach. So then which one is good here? Whether we have to go for cross-validation 1 or cross-validation 2. If we are going for a cross-validation 1, we have to evaluate the our breeding population or test population. Again, we are spending same resources to evaluate except for the primary traits. So then in what situation this approach is useful? This approach is useful if your main trait, a primary trait, is a post-harvest trait or a quality trait, where you need to spend a lot of resources to evaluate the quality trait. So in that case, if you can use your phenotypic information from the test population and the training population for the secondary traits and primary trait information from the training population to predict the quality quality trait data in your test population, that is possible. But still, it's a resource consuming approach. The second one, the second cross-validation approach, where you have phenotypic information of primary and secondary traits from the training population, you can use it for the predicting the test population. So I feel this is a better approach than MTCV, this cross-validation approach one. But cross-validation approach is also useful when your primary trait is very difficult to phenotype. Okay, so it is possible to use correlated traits to predict the primary traits using the genome-wide selection. So now we also do a lot of GWAS studies to identify markers that are associated with the traits. What we did for the first time, we used this associated markers as covariates to predict the performance of the progenies. So how we use this covariates? The marker effects, the markers that we found associated in the GWAS study, we use them as covariates while estimating the marker effects. So that increased, when we use them as covariates, that increased the predictive ability. So that increased predictive ability increase our identification. Selection decisions are changed, right? So when there is good prediction accuracy, selection of the good candidates will be possible. So genome-wide selection can also be improved using the results that we get from the GWAS. When you do GWAS, when you have a diverse population, we do GWAS. So that population can be used as training populations to predict the performance in the breeding population, and using the associated markers as covariates while training the GS model. So is it required to produce fresh training population every time that I go for genome-wide selection? So it's a question. That depends on land. So breeders, what they do every year, they do crossings, they produce progenies, they carry forward them till their homozygous condition. So if you have a proper plan, that like you produce some crosses and you're progressing, you identify best progenies and use them as at least one of them as parent in your next year hybridization program, that produces that will develop a link between the populations developed in different cohorts. So that means there is a relatedness between your complete populations. So one parent is common, you are bringing other parent to increase the genetic variance. So even then you have a connection between your population, this kind of connections. So you can use some of your progenies as training population to predict your next populations. You don't need to develop training population every time. So once you select the progenies here in the in this last 7-8 years, 7th and 8th years cohorts, you can use the selected individuals and bring back them into your training population. So when you choose parents from your available populations, you can use those available populations as a training population to predict your progenies in the coming years. So the message here is you don't need to don't need to select training population every year, but the main important thing is you need to maintain proper connection between the training population and the breeding population. So here is one approach that we planned, like how we can integrate GS in our regular breeding programs. So what we do, we choose best performing lines or elite lines from the germplasm resources. So best performing lines for the trait, and we cross to develop elite progenies, right? So what we can do is we can go for multiple crosses, develop so many progenies. Say here I'm giving an example of 2000 progenies, 2000 lines, and from that 2000 lines, multiply the seeds and use around 300 to 400 lines for the phenotyping in multiple locations. We can go for precision phenotyping here. If you have a facilities for phenomics, you can go for phenomics also. Whatever the way you use, phenotypic data should be very much precise. That is most important. And genotype all the lines and develop a GS model based on this 300 lines and predict rest of your 1700 lines using the GS model. Estimate their genetic value. If the genetic value is really, really good to go for national testing, you can directly nominate your good lines to national testing. Or if it is not that much good, you can bring back them, cross them, produce the new base population, and select from there. So that is the way we can integrate GS in our regular breeding programs. So with this, I would say if you are already breeding, doing a breeding work, you have breeding populations, how you can integrate the GSAs. If you have a population, and just try to find different populations and how they are connected. You can do that based on your pedigree, or you can also do, if you have a marker data, you can see how those populations are related using the marker information. You just estimate the average relatedness between the populations and divide them into training and test populations. You don't need to have thousands of individuals in training population. Only thing is, you have to have model that should be fitted well. So you need to have at least in rice, you need to have at least 200 individuals to build a good GS model. From then, you can predict any number of individuals. You don't have to have any limitation on breeding individuals. Only thing is, a relationship is the key. So from then, you can choose based on the genomic values, and you can use them for further breeding program, or you can also send it for national testing. This is how we can integrate in the regular already available breeding programs, integrate the genomic selection approach in already available breeding programs. I would say this is what I wanted to convey. The breeding earlier was just selecting the best and cross the best and expect the better progenies. But now, and it is not like that. Select the best, cross the best, but try to create the better. This quote, I got this quote from the Rex Bernardo's book, and thanks for listening me for this time. Thank you. I'm ready to take any questions.
Thank you, Anil sir. Participants can unmute and ask questions, or they can post their questions in chat box.
Hello.
Yes, Bharat.
Hello, sir. Sir, like, what will be the minimum prediction accuracy that we should expect in order that we should use it yes efficiently? Like, what should be that value?
I should go back to heritability. If you're choosing for the trait, what heritability you expect?
Sir,
Yeah,
for you,
I'll answer the question again. So when there is a good heritability, we say direct selection is rewarding, right? So if heritability is poor, it's not possible to go for direct selection. Here also, same way, if your prediction accuracy is too low, your selections are wrong. you will not get any good reward for the selection. So in my perspective, minimum it should be 0.4 or more.
Okay, sir. Thank you.
Okay. Yeah. Yeah.
So in chat box, we have one question which is not
Okay.
relevant to topic, but your expertise may help her to get some guidance. Scope of private sector for a student of genetics and planning after postgraduate in GPB. She has said this.
Okay. Okay. Yeah. Good, Pooja. My answer to this question is there is a goal, provided you should equip yourself that what today's industry is asking for. I have my students and juniors who had very good expertise in this like genomic selection or any other data science along with the basic principles. They were hired by good companies for the good package. Yeah, there is a good scope, but you should be equipped with what industry is looking for.
Thank you, sir.